Hello friends, welcome to Lab 3. This is Jordan Duncan again, the same TA that uploaded the videos for the previous lab. This week we're doing observations of motion, and I'm going to go through, there'll be two videos this week. This video, which kind of talks about the objectives and gives you the tools that you'll need in order to complete the lab through whether it be theory. Don't be frightened by the word theory. It just essentially means the tools that you'll need in order to complete the lab. Okay, so I'll read this kind of introduction to the inclined air track, and then I'll hit some key points as we go from section to section throughout the lab. And then I'll give you the important theory, and I'll give you some information about how you might graph your results and how you might analyze your graph in order to answer some of these questions. So 3.2. Well, the objectives are to study the motion of a glider on an incline and to understand the concepts of acceleration. Acceleration and velocity oftentimes get confused with each other, and hopefully after this brief introduction to this lab, you'll have a better understanding of the differences between those two things. So in this section, you will study the motion of a body accelerating under gravity, which, by the way, gravity is acceleration. These experiments are very similar to the ones performed by Galileo in the 17th century. He studied the motion of rolling balls on an inclined plane and deduced, among other things, that falling bodies accelerate uniformly. This lab examines acceleration more closely. You will look at the motion of a glider on an inclined air track. Okay, so let's flip this over. This is a chart which you'll be given all of the times T1, T2, and T3 for the lab, and you'll have to find delta S, and you'll have to find the average time T. And I'll discuss how you do this. And obviously you're given in the lab positions. So one of the first things I want to note is that the lab makes a couple interchanging mistakes between S1 and S2. Okay. It says position S1. For position S1, it actually means S2. And for position S2, it actually means S1. It's just the printed error. Just make sure that you switch the positions S1 to S2 and S2 to S1. And the reason we're doing that is because if you notice in the lab, it tells you to take S1 minus S2. And if you do that with the way that they have position S1 and S2, you'll notice you end up taking S1, which is a smaller number, minus a larger number, and you'll end up with a negative number. Okay? And then there's a couple other places throughout the lab where they actually misquote these. And so if you just swap S1 with S2 and S2 with S1, just swap these two, then the lab will work out perfectly and you won't have to worry about any of the mistakes that the lab had made with those terms. Okay? So position S2 and position S1. Well, what is position S1? Position S1 is the initial position of the glider. So we're going to be using a glider and sliding it down and basically an air ramp. And so the initial position that this glider is at, which would be right here, the tip of this arrow, is the initial position of the glider. Okay? Position S2 is the final position in the glider, located at the bottom of the ramp by the second photo gate. So in this lab they use what's called a photo gate, and there'll be a photo gate at each side. Let me slide this down a little bit. There'll be a photo gate at each side of the ramp, and when the glider passes the first one, a timer will start, and then a timer will click off once it gets to S2 here, which is the position of the second photo gate. When the glider passes photo gate 1, it starts the timer. When it passes photo gate 2, it stops the timer. And then you're able to record times. This looks like it's a little blurry. Let me see if I can. Kind of want to zoom this guy out just a little bit. Maybe give us some. Maybe I can't do it. Maybe I can't do that. Okay. Well, we'll just have to work with what we got. So yeah, that's the general setup. Times 1, 2, and 3, as you'll notice here, will be given to you. Those will be recorded. Another TA is actually doing the recording of what you would do if you were actually physically in the lab, and he's going to give you results for T1, T2, and T3 for each one of these independent cases. Okay? And then you're going to need to calculate the distance, which is the change in S. Okay? And we've wrote here that the change in S is S1 minus S2. So in order to find out what this first term, change in S, is, you'll take S1, which is 20, minus S2, which is 10. So 20 minus 10 is 10. So delta S in this case would be 10 centimeters. That's how far it has actually traveled in the time T. Okay? The average time T is just T1 plus T2 plus T3 divided by the number of trials. Well, we did 3 trials, so it's divided by 3. Okay, so that will be your average time T. And you're going to do that for each and every one of these cases for the first part of the lab. Okay? Then the lab is going to ask you, let's go to the next page. After you calculate the change in S with your T's and your distances, you calculate your average T, and then you calculate your change in S, the lab wants you to using the graph paper, which is at the back of the lab, it wants you to carefully graph the change in S versus T. Change in S is just change in distance versus time, okay, using the average T. So when you do that, make sure you're not using any one of these single T's, but you're using delta S and the change in time, okay? So this average change in time is what you want. And it explicitly says that, so you'll lose points if you don't use that. So after you make the graph, it wants you to draw a smooth curve through the data points. And it says, remember, you don't need to hit each one. Just give a good idea of what the trend is with your line, okay? So what does that mean? Well, these words can get a little bit confusing when it says draw a smooth curve. When you think about a smooth curve, that can be a little bit weird to think about. But I'm gonna pull a little graph over here and show you what you'll be doing. So for the first one, you're going to have a graph where you have a distance versus a time, okay? And it has you plot points. Now, this graph doesn't necessarily relate exactly to your graph. You're going to have different points. So don't just like look at my graph and then decide that this is what your graph should look like and just do this, because you'll lose a lot of points because this graph isn't going to look exactly like your graph will look when you plot your points. But what you'll notice is, like, throughout this lab, these different points you get. Now let's actually label these axes, okay? So you'll notice on the y-axis we have a distance, and on the x-axis we have a time, okay? So let's put in some arbitrary values for distance and time. Let's go easy here and say 1 through 5, and then let's go by terms of 5 up the y-axis. Okay? Now, I have a ruler around here somewhere. Here it is. And remember, it says it wants you to draw a smooth curve. So what it explicitly doesn't want you to do is to just draw and connect the dots between these lines. It doesn't want you to connect dots. It wants you to draw a trend line. So it wants you to draw a line of, sometimes called line of best fit. So we're going to try to draw a line through these points that's a straight line. So what we'll do here is start from this point, which is the corner of the graph, and then kind of look and try to draw a line that goes through the center of all your points. So this would be like a trend line or a smooth curve. Okay? And you'll notice that although the points on our graph don't exactly touch this line gives a general idea of what your points look like. Okay? So the lab asks you, let's go back to this really quick. After you do this, distance versus time graph, it asks, what is the average speed of the glider during the last run? Okay? So if you want to calculate an average speed can be calculated by the distance divided by the time. Okay? So if you want an average speed, you're just going to take the distance traveled divided by the total time, which is just, in this case, you just have d or s divided by the total time. Okay? So if you traveled some distance, average time, you should know how to calculate this based on distance divided by total time. Okay? Use those two terms. Now the lab, in addition to an average, okay, it wants you to do what's called an instantaneous speed. Okay? Instantaneous speed and average speed are not the same, right? So the average speed is essentially over the entire time. Okay, so if you were to average how fast you're going over this entire time, it would be different than picking one point out on a graph and saying that what is the speed at that point. So a speed at one point is not necessarily the same as the speed over the entire portion. So what we're going to try to do here is I'm going to give you some tools to investigate what's called instantaneous speed. Remember, I just told you what average speed is, and they're not necessarily the same. Okay? So what we'll do here is find the slope of a tangent line. So when we look at the graph we just drew, for those of you that say, oh man, those words, I don't like the sound of them, it's not as bad as you think, I promise. So what we'll do here is we'll look at the entire portion where it contains all the points from our graph, and we're going to do what's called find the slope of this line. Now tangent lines are always like a linear straight line like this, so a tangent line to a curve, which I'll show you in just a moment. But for now I just want to show you how you find the slope of a line itself. So to find the slope, you're going to do, some of you may remember rise over run. Okay, so let's go up here, close to 1, which is about right there. Now, I'm not the best at drawing graphs or being super accurate with this stuff, but what you want to do is you want to draw a triangle. So we're going to draw the triangle at 5. Just connect it up here like this. Okay. Now, rise over run means run is across the x-axis, or in this case, x relates to time and y relates to distance. So the run goes from 1 to 2 to 3 to 4 to 5. But even though there's 5, you can count 5 things here, the distance is 1, 2, 3, 4. Okay? So the run is equal to 4. In this case, it's seconds, so 4 seconds. the rise is equal to what? Well, to get a pretty good idea, we have something close, a little bit less than 5 or 5. In our case, it's kind of meaning to be 4 or 5, say like 19 or something. So let's just say that this is equal to 16 meters. Well, that's because we've measured a distance in meters. Now for your lab, you'll notice that these units for your lab are in centimeters and also seconds. So don't use meters unless you want to convert. You're more than welcome to convert centimeters to meters, but make sure you do the conversion, because you should expect your results to be the same as your graph or show the conversion for a change in units like this. So let's just get rid of that for now, not to confuse you. And the slope, I just realized that this wasn't on here, but all I did was say, the distance is equal to meters here and not centimeters. In your lab, it's centimeters. So if you do this part of the lab and you want it in meters, make sure that you show me the conversion. Otherwise, your units will be off in the end. So, but your lab is in centimeters. Just remember that. So the slope is equal to, I'm sure most of you have heard this at some point in your life, rise over the run, which is equal to, well, the rise is 16 meters and the run is 4 seconds. So the rise is 16 meters divided by 4 seconds. And what you'll notice here is that this slope, well, if it's 16 meters over seconds, well, meters divided by seconds, what is that? That's a velocity, okay? A velocity, or a speed. Speed is a better term because we're not talking about direction specifically here. So 16 meters divided by 4 seconds is equal to 4 meters per second. So that's your speed. So what does this tell us? This tells us that when we look at a distance divided by time graph, and we find the slope of the tangent, okay, which I'll show you the tangent in just a second, that tells me that that is a velocity or a speed. Okay, so what happens if you don't have like a perfect straight line like this? Okay, so to find the instantaneous, let's make sure that I get this all the way in here. Okay. So it wants you to, the lab asks you to find the instantaneous speed. Okay? And it tells you to pick 3 points, one at the beginning of the graph, one at the middle of the graph, and one at the end of the graph. Now your curve might not look like this, but say you have a graph that does curve like this. The slope of the tangent, so let's, just to connect the dots here, let's go back and look at what the lab asks you to do. It says, you have seen that in class the instantaneous speed can be found from the slope, which we just talked about, the slope, of the delta S versus t graph, okay, which was the graph before, distance versus time. Pick 3 approximately even space values of t on your graph and cover the whole range of times measured in the experiment. That is, pick points at the beginning, the middle, and the end. At those 3 points from the graph, draw a tangent line to the smooth curve you drew through your data. Okay, so I'm not going to do that on because I didn't actually plot points for your graph exactly. Okay, so what I'm going to show you is, well, what is a tangent line to a curve, and how do you find the instantaneous speed at that point? Okay, so find the slope of the tangent line at each selected time. So I'm going to pick 1 point, and you'll have to do it for 3 points on your graph. But for 1 point, let's take a look at what that might look like. So on this graph, you'll notice here I've picked a point. Okay, and this is, I wrote x and t here. So x just means the distance in x, okay? And t just means time in seconds. Okay, we talked about before that slope is equal to the rise over the run. Okay, how do we find that on here? Well, our goal is, once we have our point, using a ruler is very helpful because drawing tangent lines can be difficult. The idea of a tangent is you want to draw a line such that the line only intersects with the curve that you're drawing a tangent to in one spot. Okay, so we want to know how to find the acceleration, not the acceleration, the instantaneous speed at this one point. So I'm going to draw a tangent line here, and you'll notice that obviously my fat pen has leaked over into my line a little bit, but just ignore that. Imagine this straight line only touches this curve at one place. Okay? So what you'll do again is you're going to draw your triangle. So treat this line like the straight line in the previous graph. And we're going to draw another triangle on this graph here. Okay, so you notice this looks similar to what it looked like before. Now, you'll notice that part of this, this line here that we've drawn, this checkered line, is actually parallel to the t-axis. So if we were to draw something down like this, we would be able to determine what's called the change in time. Okay, so this would be like t1, and this would be like t2. And to figure out this line, you would write t2 minus t1. Okay, so t2 minus t1. And then for this portion, well, this axis is an x, so this would be like doing x2 minus x1. So our slope is equal to rise over run. Well, our rise is x2 minus x1. So we're going to write x2 minus x1. And our run is like t2 minus t1. So in your lab, it asks you to choose 3 points and to find the instantaneous velocity, or not acceleration, instantaneous velocity or speed at that point. And that's exactly what we've done here. If you have a distance versus time graph and you choose a point, the instantaneous speed is drawing a tangent to that line and finding the slope of that tangent. So that's all we've done, is draw the tangent line and we found the slope, which is rise over run. And that tells us that this is equal to our, I'll make sure this is in the picture here, instantaneous speed. Okay, so for this graph, at this point, the slope of the tangent is equal to the rise over the run, which is equal to our instantaneous speed. Hopefully that makes sense. You'll be doing something like that on your lab. Okay, so now we know how to find our average velocity or speed, and we also know how to find our instantaneous velocity. And this is just talking about basically the things that I just mentioned. And then once you find those 3 points, the instantaneous speed at those 3 points, it asks you to plot those. So this is the speed in centimeters per second, again the change in the distance, and then the change in time, which if you go back to the graph we drew, actually I think it's under here, you'll see that this is distance, this is time, and that this is the change in distance, and this is the time in seconds, and then calculate at those 3 points what your instantaneous speed is using your 3-point method. So this is just 1 point, but you would do a point here, say, and a point here, and then you would draw a tangent line, to the curve here, and a tangent line to the curve here. You'll notice that these lines change. They're not always going to be in this direction, but they'll change because they're going to be tangent to this curve, and the curve is changing. So this one will look like this one looks like this, and this one looks like this. And you would just draw your triangle the same way here. Just draw your triangle. You'll notice that the change in the x values aren't as much, but here the change, the change in the x is going to be a lot more, and the change in the t is going to be, a lot less. Okay? Hopefully that makes sense. I didn't confuse anybody. Okay. So that's great and all, right? So now we understand some things about instantaneous speeds and average speeds. But what does it mean when we start talking about acceleration? Okay, concept of acceleration. This says we can define acceleration to mean the speed of the glider increases as it moves down the track. The speed of the glider changes with respect to position and time. If you think about it for a minute, you'll find that this is ambiguous. Galileo had to struggle with the idea of acceleration. So you're in good company. A lot of us, the first time we hear about acceleration, we've heard about it forever, but we don't really understand what it means exactly and how it relates to velocity. So the definition of an average acceleration over time, over some time interval, TF. Okay, so TF just means the final time. So the time when the cart gets to the bottom of the track. And T initial is, well, what time was it when we passed the first gate? So what time was it at the very beginning? Well, that was time initial, T equals 0, and time final, however long it took you to get down the track. Okay, so don't be confused by the little F's and I's. They're not too difficult to keep track of. So this would be acceleration is equal to the final velocity minus the initial velocity. In our cases, we're using speeds, divided by the final time minus the initial time. Again, it says where VF and VI is the change in speed over the interval. Here, TI and TF are the beginning and the ending of the points in the time interval. So just like I said. So using the data you recorded in Table 2, make a graph showing the speed of the air glider versus the total time t the glider has moved. And then again, you're going to draw a smooth curve in the same fashion that I showed you in the beginning. Okay, so let's think about acceleration really quick. So a lot of us have heard about acceleration, but are unclear about exactly what that means. So a change in velocity over time is what we call acceleration, or change in speed over time. So if you had a Ford Mustang, many of us have heard like, oh, how fast is your Mustang, or how fast is your Jeep? Well, a Ford Mustang, now this may or may not be true. I'm not sure how long it takes a Ford Mustang to go 0 to 60, but this is just an arbitrary time. For instance, a Ford Mustang may take 3 seconds to go from 0 to 60 miles per hour. And that is what we call an acceleration. So how do we write that in terms of like math or physics? How do we represent this? So this is what you would call an acceleration. So acceleration is equal to the change in the velocity over time. Okay? So this little symbol right here that I'll draw just means change. Okay? It means change in the velocity with respect to the change in time. Well, change just means that you have, like before, your velocity final minus your velocity initial divided by, again, I keep saying velocity because I'm using them interchangeably, but this represents speed. Speed is just, velocity without a direction. Velocity is speed with some direction. Basically, you're driving 20 miles per hour in the eastern direction. That would be a velocity. Okay, speed would be you're driving 20 miles per hour. And then your change in t would be t final minus t initial. Okay? Which is equal to, well, in this case, our final speed is 60 miles an hour. So you're just going from 0 to 60 because your initial velocity was 0 and then your final velocity was 60. Initial, final. Okay? And then you're dividing that by, well, how long did it take? It took 3 seconds. So that's all an acceleration is. And this is also miles per hour. Now, these units, don't worry about the units. I'm not going to show you how to get from miles per hour to something that relates a little bit better to seconds, but you can use some dimensional changes. You could change. We're not even going to talk about it. You're not going to have to worry about it right now. So that's what acceleration is at the most basic level. And then the lab asks you again to do something. It says, let's make sure we're in the frame here. Using your data you recorded in Table 2, make a graph showing the speed of the air glider versus the total time the glider has moved. And draw a smooth curve. So now it wants you to, instead of doing a distance versus time graph, it wants you to do another graph, but this time a speed versus time graph. So this is different, right? Because now on this y-axis we have these speeds, v1 and v2, and we have these times t1 and t2. So this axis is the same, but this axis has changed from a distance to a speed. What does that tell us? What can we get from that? So again, what we'll do is, let's say we choose a point here and a point here. We're going to do the same exact thing we've been doing, and we're going to draw ourselves a pretty little triangle here. Okay. Well, again, this is a straight line velocity or speed versus time. So we're going to have a run, and we're going to have a rise. Well, our run relates to t's, and our rise relates to v's, which is speeds, and t's are times. So what is the slope? The slope in this case, again, I wrote meters per second here, and I think your speed in the lab is centimeters per second. So if you write meters per second on your graph, you need to show me the conversion from centimeters to meters. Okay, don't just like arbitrarily write meters per second when your measurements are in centimeters. Okay? So again, we have a slope, which is equal to the rise over the run. And in this case, we have a rise, which is v2 minus v1. Okay? And we have a t, which is t2 minus t1. So v2 minus v1 and t2 minus t1. Well, let's move these guys up into our slope form where we have a rise and a run, and a rise over a run, we have v2 minus v1 over t2 minus t1. So for a velocity versus time graph, when you do the slope of a tangent, okay, when you find the slope on a velocity versus time graph, it's going to equal your acceleration. Or better yet, if it's at a single point, it's going to be equal to your, so if this were a tangent line, it would be equal to your instantaneous acceleration. But for this graph, since I've been doing this for a while now, so I feel like the video is getting kind of long. But you would do the same thing if you had a curve. So say you had some curve that went like this. If you wanted to find your acceleration at that point, you would do another tangent line to the curve, draw your triangle, do your run and your rise, and it would tell you what the instantaneous velocity is at that point on this curve. Okay? And I'm trying to think, I'm not sure there's much else to tell you. So let me just wrap this video up by showing you a little key points to take away from this. So delta S is equal to S1 minus S2. Now, if you write S2 minus S1, it's not wrong, it's right, but you're going to end up with a negative number, and you can just neglect the negative number, and it'll give you the same. So like 10 minus 20 is going to be equal to minus 10, or 20 minus 10 would be equal to 10, and you could just get rid of the minus sign and you would have the same result. Okay, so average speed is equal to distance divided by the total time. The instantaneous speed is equal to the slope of a single point on position versus time graph. We talked about that. The average acceleration is equal to the final velocity minus the initial velocity, or final speed minus the initial speed divided by the time. Instantaneous acceleration is the rate of change of velocity at a specific instant in time. With those tools, you should be able to complete the lab. That's pretty much the gist of what it has you do. There's a series of questions that it'll ask you, some of which relate to what I specifically taught you today, and some of just like critical thinking, that you should be able to answer without anything that I've given you here today. So thank you for your time. Enjoy the lab, and make sure, and I forgot, but one thing we need to mention is that when you submit these labs, if you submit a file, like say you submit a file that's 15 images, it's really difficult to grade 15 separate images, especially if they don't have names. So there's two things that, as a grader, that we really would like for you guys to do. And one is to make sure that your images are oriented, in the proper position. Like if we get a submission and this is the way it's oriented, it's really difficult because in D2L itself, we can't just like choose to rotate the image back. We would have to download all of your images and then manually rotate each image. So it gets really overwhelming, and it takes a long time to, if your first image is like this, and then your second image is like this, and your third image is like this, and your fourth image is finally right side up, it's very difficult to grade. So we ask that you please at least orient your images correctly. And what we'd really like for you to do is, most people have iPhones or Androids, is download an app called Cam Scanner or a similar app. So Cam Scanner is a good app, at least I know for sure on an Android. I'm pretty sure it's on Apple devices as well. But download this app, so when when you open this app, you can actually choose to save your images as a PDF. So when you take images, you can save them in a single file. And it really helps us because if you upload a cam scanner or a similar scanning app on your phone's PDF files in D2L, it actually shows up nice and pretty. And it's really easy to reorient your pictures to make sure that they're, you know, not like this when you submit them. And it's also, you're just uploading one file instead of uploading 15 different files of images. So we would really appreciate if you could just limit the number of submissions that you do, and if you can, use something like CamScanner to convert it to a PDF file, which it does automatically when you save it in CamScanner. And if you don't know how to do anything from CamScanner, you can just share. There's a share button in here, and you can just share it, send it to your email, and then save it to your computer if you don't know how to do it from your phone. But you can easily just save it to your phone as well and then upload it from your phone directly to D2L. Okay? This would be very appreciated. All right. Thank you. Bye.